Okay, we're moving into our new chapter. We are in rational exponents, radicals. This is your exponential kind of unit. It's a combination of a couple different things. So the first thing we're talking about are rules of roots and rational exponents. These numbers up here, guys, you should be able to do these and more from memory. So you should know all your perfect square number 1 through 20 and your perfect cube numbers, probably 1 through, if you knew 1 through 10, that would be good. You can do these things a lot quicker if you know those from memory. We're going to go through these. This is a review, this top part. We're simplifying root 32 the efficient way. You can think of the largest perfect square number that goes into 32, which would be 16. So that's 16 times 2. So root 16, that's 4 root 2. If you don't know your perfect square numbers, then you're going to have to do your factor tree. 2 times 16, 2 times 8, 2 times 4, and 2 times 2. And we need groups of 2. So for every group, 1 comes out, so that's 2 and 2 on the outside, so that's 4. And then this 2 right there stays under. So this is much better to do it that way. 4 to the negative 2, remember if it's a negative exponent, you flip the base, so that would make it 1 over 4 squared. It's 1 over 16. 4 raised to the 1/2 power. Whenever you see anything raised to the 1/2 power, that is taking the square root. So 4 to the 1/2 power is really the square root of 4. That's 2. This negative does not go with the square. The only thing that is raised to the 2 power, that's 7. That's 49. You pick that negative up last because it's not included. Here's the difference between parentheses and no parentheses. On the E, the negative is also being squared, so that would be positive 49. This is multiplication, so if the bases are the same, you add the exponents. So this is x to the 6, y to the 3, y to the 5, so that's y to the 8. So when it's multiplication with like bases, you add the exponents. When it's division with like bases, you subtract the exponents. This is with like bases. If it's 2 exponents, this is power to a power, and that would be multiplication. So make sure that you can identify what kind of problem it is. Makes it a lot easier. This is power to a power. Power to a power because we have an exponent on the outside of the parentheses. So I have to distribute this 2 right here. So this would be x to the 4th, y to the 6th. This is division. So I'm going to subtract. And I'm going to put my answer wherever the largest exponent is. So between the x's, the largest exponent is in the numerator. So I'm going to put my answer in the numerator. So 7 minus 4, that's 3. The y's, the largest exponent is the denominator, so I'm going to put my answer there. So 8 minus 3, that's 5. We do not want to have any negative exponents. This is power to a power. Make sure everything has their own exponent. So that 3 goes to both x squared and y1. So it would be like this. This has a negative exponent. The order doesn't matter. You can distribute first. If I distribute first, I would get x to the negative 6, y to the negative 3. I cannot leave it like that because they're negative. So if it has a negative exponent, you're going to move it to the opposite place that it's at. So you either have it in the numerator or the denominator. So this one, I'm going to move the x6 down, and I'm going to move the y3 up because they're both negative. The addition, subtraction, the same number has to be under the radical, so this would be 7 root 3. You don't change it. If it's multiplication, you multiply outside times outside, inside times inside. This, you cannot leave that radical on the bottom, so we have to swing it up to the top. So that would be root 2, and square it on the bottom, so that's 2. That's just a quick review. All right, so now this is new material. Okay, this, we are changing it from rational exponent form, which means the exponent is a fraction, and we're going to change it to radical form. Okay, rational exponent and radical form, they're inverses of each other. You have to be able to change it back and forth real easily. If it's in one form and you can't solve it, put it in the other form. So these are all in rational exponent form. We're going to move it and change it to radical form. So how you do that is you put your radical. This base is the number or variable that goes underneath the radical. That denominator becomes the index. The index is the number inside the radical. This 3 stays in exponent. This is rational exponent form. And this is radical form. So put your radical, y comes under, 9 is your index, 7 is your exponent. This, I'm going to first change this to y to the 1/4 because it's negative. And this would be y 4th root exponent 1. The x doesn't move because it doesn't have a negative exponent. This would be the square root of xy. Now we're going to go reverse order. We're going to write this in rational exponent form. So this base still is the base. I'm going to put it in parentheses. The exponent comes with it. This becomes the denominator of the exponent. xy 4. The exponent, the 8, that's the denominator. And the exponent is 1. And it goes 1/8, it goes to both xy to the 4th because it's both underneath the radical. And then I can simplify that. X to the 1/8, y, 4 times 1/8 is 1/2. This would be -5. The 6 stays, and that 3 is your denominator. So it's -5 squared, which is 25. x10y is what's underneath the radical. This is your denominator over 1. So x to the 10th times 1/5, that's x squared, y 1/5. Okay. All right, we're going to solve these without a calculator. Okay. Now, what you want to do is get in the habit of reading it in a way that you can do it without the calculator. So if this is in rational exponent form, well, in rational exponent form, 27 raised to the 4/3 power, that would be difficult. But if I change it to radical form, what that means is the cube root of 27 raised to the 4th power. Well, I don't want to raise it to the 4th power first because I'm going to get a really big number. So what I'm going to do is take the cube root of 27, which is 3, and then I'm going to raise that to the 4th power. 3 to the 4th power, that's 81. this reads the fourth power of 16 raised to the fifth power. Again, do not do 16 to the fifth power. Take the fourth root of 16, that's 2. Raise that to the fifth power, it's 32. This one, square root 4, that's 2. This is 4 raised to the negative 2 power. It's a negative exponent, so I flip the base. I square it, 1 over 16. This is 4 to the negative 1/4. The base flips, taking the square root, 1/2. This is negative exponent. I flip the base. This is my taking the square root, and I'm going to cube it. So square root of 1/9 is 1/3 cubed, 1 over 27. Anytime you have a power of 10, you count the number of zeros. There are 6 zeros. This reads the 6th root of 1, 2, 3, 4, 5, 6, and then you pick up the negative. The 6th root of anything with 10 zeros is 10. This would be negative 10. This is taking the 6th root of a negative number. You cannot take an even root of a negative number. This is not possible. This is the 5th root of negative 1 and 5 zeros. You can take an odd root of a negative. This would be negative 10. Okay. When you're using exponents, the same rule applies with, first of all, you can't have a negative exponent. Second of all, you cannot have a rational exponent in the denominator, because that's like having a radical in the denominator, and you cannot have a radical in the denominator. So we have to simplify this. We want our exponents to be positive, and we want to rationalize if needed. So I'm going to move my x down to the bottom because it's negative, and I have x to the 3/5. Well, I cannot have a rational exponent. I need to do what I need to do to make it equal to the next closest whole number. Okay, and you're going to always go forward. So 3/5, if I add 2/5, and when you're multiplying, you're adding the exponents. So when I add or multiply by x to the 2/5, and I have to do it the same here, this is going to become x to the 1. So now I have on the bottom x squared, because I have this x and this x. Okay, this is the only time when you're going to have more than one of the same variable. We have an x on top and x on bottom. But if we combine and subtract 2 minus 2/5, we're going to end up with another rational exponent. So this is going to be your answer. Okay, so I'm going to first take care of my power to my power. I'm going to multiply 1/4 times negative 4/3. The 4's cancel, and you get negative 1/3. I'm going to flip my base because my exponent is negative. And this means I'm raising it to the 1/3 power, which means I'm taking the cube root. So the answer is 2/3. Remember, if you cannot do it in one form, change it to the other form. So I'm going to combine my x's. So I'm going to add 2/3 and 5/9. So I need a common denominator. This would be 9. It's 6/9. So 6/9 plus 5/9. That's 11/9. And then I have 1/5 1/3. Common denominator is 15 times 3. This is 3/15, and this would be 5/15. So we have 3/15, 5/15. Okay, so you put it's division, you put your answer where the largest fraction is, so that would be on the bottom, so this would be y 2/15. You cannot have a rational exponent in the denominator. I need to go to the next whole number, which is 1. I need 13/15. So I'm going to multiply that by y raised to the 13/15, and I'm going to multiply this by 13/15. I'm going to end up with 1y here. So y is on the bottom. On the top, it's going to be this. And that's my answer. Remember, you cannot have radicals on the bottom. You cannot have rational exponents on the bottom. Here are your properties of radicals, and we've already talked about exponential. Now radicals contain fractions. Here's all your rules that we've already talked about. Okay, so now we're going to do radicals. If the number underneath the radical is not the same, you can multiply. It only has to be the same when it's addition and subtraction. So we have 2 times 5, that's 10. Okay, 6 times 12 is 72. I need to think of a perfect cube number that goes into 72. So our lowest perfect cube numbers, we can make a list right here. 1 cubed 1, 2 cubed 8, 3 cubed 27, 4 cubed 64, 5 cubed 125. Okay, well, what is the smallest number that goes into 72 out of this list? That would be 8. So 8 times 9. So the cube root of 8, that's 2. 2 times 10, that's 20. And this is what you have left. If you have the same number in the index, they're both fourth root, I can put them under the same radical and simplify first. 80 divided by 5, that's 16. The fourth root of 16 is 2. If it's the same number in the index, put them under the same radical. This is 6 times 4. And I can also put 2 in there. So it's like that. Oops, this is supposed to be 6. Okay, then I'm going to simplify 2 and 4. That leaves me with 2. So I have the cube root of 12. And I can't simplify that. Cube root of 120, I think of the largest perfect cube number. It's not going to be 27. 8 goes in there. $15. So the cube root of 8 times 15 would be 2 cube root 15. All right, since the bases are the same, I can add my exponent. So this is going to be 16 7/3 over 2 7/3. Okay, I'm going to make my bases the same. This 2 and this 16 don't have the same base, but I can change it so that it's like bases. So anytime you don't have like bases, and if you can change it to like bases, we want to do that. So 16 is equal to 2 raised to the 4th power. So I'm going to come over there, and I'm going to change 16 to 2 raised to the 4th power. Everything else stays the same. So I get this. Well, this is power to a power, 2 to the 4th raised to 7/3. That would give me 2. 4 times 7 is 28 over 3. And then I have like bases, so I can follow the rules for division, which is subtract the exponents, and I get 2. 21/3, which is 2 to the 7th power. 2 to the 5th is 32. 2 to the 6th is 64. This is 128. So you keep simplifying until you cannot simplify anymore. If you need to switch up with exponential rules and rational rules, then you need to keep changing it until you cannot simplify anymore. So the indexes are the same on the top. This is the cube root of 18 times 3 is 54. The largest perfect square number would be 27. 27 times 2 is 54. So this is 27 times 2. So it's going to be 3 cube root 2 on top. On the bottom, we have indexes are the same. They can be put under the same one. And you get the 6th root of 4. Okay, so I'm left with this. Okay, I can't do anything else to that if I leave it in radical form. So I'm going to see if I can do something in rational exponent form. So this would be 3 times 2 to the 1/3. Because remember, this becomes the denominator. That's the numerator. This is 4 to the 1/6. Well, I'm going to change these bases. 4 is equal to 2 squared. So that means this on the bottom is going to be 2 squared raised to the 1/6, which is 2 to the 1/3. And now I can cancel that, and my answer is 3. You keep going until you can't go anymore. Okay, I'm going to take the 4th root of this. So the 4th root of 32, I need to think of a perfect 4th number that can be raised to the 4th power. Well, 16 is the perfect 4th root number. 16 times 2, the 4th root of 16, that's 2. Okay, and I have this 2 left over, so it stays under. Now, to do your exponents, what you're going to do, x to the 6 looks like this. 1, 2, 3, 4, 5, 6. Okay, I need a group of 4 that are the same. Here is a group of x's, a group of 4. That means out of that group of 4 x's, one of those will come out. Okay, so I'm not going to want to write those x's out like that. So what I'm going to do is I'm going to divide by 4. I want to know how many whole groups there are. There's one whole group, but there's these 2 x's that are left over. So they got to come back underneath the radical. So we divide by 4 again. How many whole groups are there? There's one whole group with 1 left over. 12. How many whole groups are there? There's 3 whole groups. That's my answer. Now we're doing cube. What perfect cube number goes into 40? That would be 8 times 5. Perfect cube root of 8, that's 2. And we have our 5 left over. Now we divide all these by 3. How many whole groups of x's? There's 2 whole groups, 1 left over. There's 4 whole groups. There's 1 whole group and 2 left over. Okay, we want to have, this has to be the same number because it's addition. I can break this down and I get 2 cube root of 5 plus 2 cube root of 5. That's equal to 4 cube root of 5. The fifth root, okay, we cannot, I'm going to change this to rational exponent form because I like it better. This would be 8 to the 1/5. Okay, I cannot have that rational exponent. I've got to multiply this by 8 to the 4/5. So I get 8 to the 4/5. So I end up with an 8 on the bottom, and 7 to the 1/5, 8 to the 4/5. Okay, I've got to put it back into radical form because that's how it started. So this would be 5th root of 7, 5th root of 8 raised to the 4th over 8. Okay, I can't leave it like that. The 5th root of 8 to the 4th. Okay, this is what I'm going to do. I'm going to break this 8 down the lowest that I can. So that 8 would be equal to 2 to the 3rd. 8 is equal to 2 to the 3rd, and that's raised to the 4th power. Okay, so we have 5th root of 7 is going to stay there for a minute. This now becomes the 5th root of 2 to the 12th. Okay, and the reason why we're doing that is because I would have to raise 8 to the 4th power, then take the 5th root of it. Well, we're going to follow those rules that we did a while ago when we divided up here, right here, for our exponents. We divided the exponent by the root. Well, 12 divided by 5 will give us 2 whole sets of 2, and we have 2 sets left over, 2 2s. So I'm going to end up now with a number that's more manageable. I get 2 squared is 4, and then underneath the 5th root, I have a 7, and I have 4. So this is going to end up being 28. And it's over 8, which means I can simplify, and you're going to get the 5th root of 28, which I cannot simplify anymore. Okay, this one, I'm going to break it apart because I can't do anything the way it is. So we have the cube root of 4 over the cube root of 9x. Which means I'm just going to leave the cube root of 4 because I'm not going to do anything to it. This is 9x to the 1/3. I have to make that 1/3 equal to 1, so I need 2/3 more. So I'm going to multiply this by to the 2/3. So on the bottom, I'm going to end up with 9x and put it back in radical form, and I get 3 cube root of 9x squared. Well, cube root of 4, 9x squared is equal to 81x squared. What is the cube root of 81? Perfect cube number that goes in there is 27. 27 times 3 is 81. So I have the cube root of 4. Cube root of 81 is 3. And I have left over 3x squared, cube root, over 9x. So I have a common index, so that means that I can multiply 4 times 3x squared. That's 12x squared. I have that 3 in the front, over 9x. This 3 cancels with that 9. Cube root of 12x squared over 3x. You just keep going until you can't go anymore. Under the same index, I'm going to see if I can combine this, which I can. This would be x10 y5 over x squared y. Subtract the exponents, and I get x8 y4. I divide both of those by 3. I have 2 whole groups of the x's, and I have 2 left over. 4 divided by 3, that's 1 time with 1 left over. That one was easy. When you have a radical in the bottom, you have to multiply times the conjugate, which for this one, it's going to be 5 minus root 3. And so my answer is going to be, for here, it's going to be 25 minus 3, which is 22. 5 minus root 3. Okay, there's O. This would be 6 plus root 2, or radical 6. So that would be 6 times, root 6 times root 6, that's 6. Root 2 times root 2, that's 2. On the bottom, you get 4. The top will end up with this. And the last one. Okay, so we have 4. All right, so the bases are the same. So all you do is add 12, 9 squared, 9 raised to the 2/3 power, which is the cube root of 9 squared, which is the cube root of 81. And that would be 27 times 3. Cube root of 27 is 3. So a 3 comes out. A 3 stays under. So this is 36, 3 to the 1/3 power. All right, that's all.